So we've done this. So let's look at this. Best time to buy and sell stock with a transaction fee. You're given the same array prices, and again you can have any number of transactions. Can't hold more than one copy of a stock. Uh, the constraint is that every transaction now, there's no cooldown period, but every transaction has a fee associated with it. The fee is actually paid at the time of selling only. So even though they say a transaction fee, I mean, you might think that every time I buy, I would have to pay it. Every time I sell, I would have to pay it. It's not like that. A transaction is basically a buy-sell uh, interval. So if you look at this toy example, the fee is given to be 2. So if you um, if you buy on this day and if you sell on this day, you would incur a profit of $7. But then you would pay a $2 fee on that. So it's $7, but you pay a fee of $2 on that. And then again, maybe you buy on the stock at a price of 4, sell it at a price of 9. You incur a profit of $5, but then you have a $2 fee. So the total profit you make is 5 plus 3, which is 8. Without a fee and any number of transactions, we would have done things differently. We would have had a transaction that goes from 1 to 3, another transaction that goes from 2 to 8, another transaction that goes from 4 to 9, and that way we would capture all the 3 rises and avoid any fall. But since we have a fee, if you look at the first 2 options here, 1 to 3 and 2 to 8, well, if I had a rise from 1 to 3, I would have a profit of $2, and then I would end up paying all those $2 as a fee. Likewise, I would have a profit of $6 here. I would end up paying $2 as a fee, so I would make $4 between these two. Instead of that, if I buy here and I just hold and I sell at a price of 8, I get $7 minus $2, just $5. So $5 is better than $4. So the strategy has changed for what I should do. For this example, and if, with a fee of $3, the maximum profit you can get seems to be to buy at price of 1, sell at a price of 10. So you have a profit of $9 minus the $3 fee would be $6. Any other way would lead to a smaller profit. And you can see that by trying other options out. So we will again do it in the same way. Since it's very late, I'll just directly describe what the thought process is, because before my brain feels even more sleepy. So we'll follow the same decrease and conquer approach. Take the overall problem and imagine, using a decrease and conquer approach, imagine a chain of managers under you. An arbitrary manager will receive a prefix of the array. up to index I, and we expected to solve the subproblem. Well, let's keep, we are preserving the same form here. So the original problem was find the maximum profit you can achieve, at the end of, day n minus 1. So we can say what's the maximum profit that can be achieved with, yeah, here we have any number of transactions like before. Ending at index I. So in order to find out how g of I can be calculated by using the work done by our subordinates, specifically the immediate subordinate, we ask what happens on day I. So on day I, maybe nothing happens. If nothing happened, the solution for my subproblem would be the same as the solution for my immediate subordinates subproblem. Again, nothing different from what we did earlier. Or maybe a transaction happened, in which case it would have been a sell transaction. So what was the purchase date? What was the buy date? Broadly, two categories. Either it was on the previous day or it was on some earlier day. If it happened on the previous day, that final transaction would have been a buy on day I minus 1, sell on day I. So the profit from the last transaction would have been prices of the delta in the price. But this time, so you have a view of this complete transaction, and so you have to now also factor in the fee for it. So your profit is now reduced by an amount that is equal to the fee. So this is for the last transaction. But before that, here there's no cooldown period or anything like that. So up to index I minus 1, what was what was the best, what was the maximum profit that could be achieved up to that point? That would be g of I minus 1. Right, the solution to the global problem up to, the global solution to the problem up to index I minus 1. It's alternatively the uh, buy date for this last, for this sell transaction was somewhere inside that, in the interior of that red rectangle. In which case, I would give the same argument for why there would be optimal. Well, actually, hold on. Before we look at optimal substructure, what we want, the information that we want from our subordinate is what is the maximum profit? What sort of, how can you arrange things so that you get the maximum profit and you have a sell event happening on day I minus 1? Because it's that, if there is sell happening on day I minus 1, that means there was a transaction that you ended there, which is what I will extend. So what I want from my subordinate is the maximum number of transactions sorry, not, just shows my brain is checking out right now. Maximum profit with any number of transactions. So ending at index I, but specifically with a sell event at index I. Sorry, not index I minus 1. Right, maximum profit with a. So I'm expecting from my subordinate, what's the best possible history up to your index, such that there's a sell happening at your index. Because I'm going to take that and add the delta in the price to get the best possible history up to my index within this subcategory where the buy happens on some earlier day, where the buy happens in your zone. So this part makes the definition of this subproblem not have the same form as the definition of the original problem. So we'll call this with a new name, f of I minus 1. So we give it a name f, and since this ends at index I minus 1, this is basically f of I minus 1. So that means g of I can be written as the max of these three. G of I can be written as the max of g of I minus 1 and the max of these two. Now we'll do the same thing as we did in the earlier problems. We'll, the delta in the price is common. Now whether we add f of I minus 1 to it or whether we add g of I minus 1 minus phi to it depends on which of those two is bigger. So the delta in the price will be there. What we'll add to it will depend on which is bigger, f of I minus 1 or g of I minus 1 minus the phi. So that's the recurrence for g, which is in terms of f, so we definitely need a recurrence for f. And as always, the recurrence for f is going to be precisely this. These two cases combined together make up the f, the whatever is the max of these two, is that's precisely f of I, because if you think of f of I as the maximum profit you can get with, I didn't write it down here, so f of I is basically the same thing, same definition as g of I, but with a sell event on day I. So if there is a sell event on day I, the question is, when did the buy happen? Buy could have happened on the previous day, in which case the profit, the maximum profit would be this, or the buy could have happened on some earlier day, in which case the best profit would be obtained by extending my subordinate solution instead of starting a new transaction. So this part is basically what f is. prices of I minus prices of I minus 1 plus max of G of I minus 1 minus the fee and f of I minus 1. And then we can write G of I as in a simpler way as just max of G of I minus 1 and f of I. These are the two recurrences we will work with. So our base cases G of 0 is obviously 0 because whenever we have only a single on the first day or on the 0th day, there's no profit. Since there was any transaction, that would have a profit of 0. And if there was no transaction, then also there would be a profit of 0. Now the f value is the tricky part here. Everything else has been straightforward. Uh, the tricky part is what f of 0 should be. If you look at the definition of f, it's the maximum profit with any number of transactions ending at index I in this. So f of 0 would be ending at index 0 with a sell event happening on index 0 or on day 0. So what does it mean for a sell event to happen on day 0? The only possible buy in that case would be at on day 0. So if you buy and sell instantly, in all the other problems it doesn't matter, it doesn't have any effect. We don't even need to worry about whether that transaction is present or not. But here, because every transaction is associated with a fee, we need to think carefully about whether f of 0 should be 0 or whether there should be a fee charged for f of for f of 0. In other words, should it be 0 or should it be a value of minus whatever the fees are for a transaction. So to think about that, let's see, if whenever we create a new transaction, we know that we add the fee or we extend our subordinate's transaction. But what would our subordinate do? Our subordinate would also do this or extend their subordinate's transaction. So what happens if our subordinates keep extending the transactions of their subordinates? What will happen at index 1 would be um, either, so think about what the first manager will do. Either start a new transaction from index 0 to index 1, in which case there would be a fee, or extend the transaction uh, from index 0, whoever the subordinate at index 0 was, with this. So if we define f of 0 to be 0, we are actually giving away free money because at index 0 there was nothing, right? Uh, no profit, and we get to extend that solution without paying a fee. So in effect, these two should be identical. If I am at index 1, whether I look at it as starting a transaction on day 0 and ending it on my day and paying a fee, or whether I look at it as extending my subordinate's solution with the delta, the answer should be the same, because my subordinate is not going to have an existing uh, transaction to extend. If at all uh, they have, it's just going to be a buy and sell that happened at the same time, and so it's a transaction that does not span any days. So if we associate that kind of a transaction, that default transaction, with a negative fee, then things would work out, because then we would know that we're not getting free money here by extending our subordinate solution, and everyone is extending, and nobody's really paying any fees. Somebody has to pay the fee for that transaction whenever it started, and whoever ended it the first should pay the fee, and that happens at index 0. So this is the tricky part. Once this is settled, then what you need to do is just create tables again. Your G table and F table, one-dimensional array, size n, initialized to 0. Let's do the same thing with F table again, but we have to ensure that this is present. And then we have our usual loop where all the managers from bottom to top calculate f of I and g of I and store them in f table of I and g table of I. So what's f table of I according to our recurrence equation? It is the delta in the price plus the max of, so at this stage I'm not even thinking, I'm just copying whatever the recurrence says it is, plus max of g of I minus 1 minus phi and f of I minus 1. That's f of I. G of I would be, as usual, max of g of I minus 1 and f of I, right? The new f of I, which is in, I mean, which has been calculated. Finally, we return g table of n minus 1. The body of the for loop runs in constant time, so the overall time complexity is order n. And the auxiliary space used is order n. Can be improved to order 1. Like before. So, any questions about this? No, okay. Yeah, Pranav.
Yes, I don't have question about this problem, but actually the previous problem, I did not understand the I minus 3. I thought it will be I minus 2 because we have only 1 day of cooling period, right? Sorry, I might be asking a stupid question. It's too late, but I did not
Yeah,
understand
yeah,
that.
that's
Sorry.
fine. No, so the thing is, when you are starting the transaction on day I minus 1. So you have to go 2 days before I minus 1. Um, so here, if I'm at index I am looking at sell event that happens on index I. When did the buy event happen? If it happened on the previous day, then this made up the last transaction from I minus 1 to I.
Mm-hmm.
So if I want to maximize the profit before that, I cannot use the G value for I minus 1 or even I minus 2 because the gap, the minimum gap between a sell event and a buy event has to be at least 2 days. Since the buy event happened on I minus 1, any prior sell event would have to happen on or before I minus 3, day I minus 3. So the gap is 2 days. So whenever you sell the stock, you can't buy on the next day. You have to buy on the day after that. So there should be a minimum 2 day gap between any sell and a buy that follows it. So if this is a buy, any sell that happens before it should have happened on day I minus 3 or earlier. Does that make sense now?
Yeah, got it. Thank you.
So there cannot have been any activity on
Mm-hmm.
days any other activity on days I minus 1 or day I minus 2.
Yeah, because
But
I minus Y is basically our buy date,
yeah,
right?
yeah,
So, and then there is a I minus 2 will be the cooldown. So I minus 3 will be the next transaction date.
yeah, or you can say the previous transaction date, the allowable, the maximum allowable date for the previous transaction would be I minus 3.
Got it. Yeah. Thank you.
Okay, so hopefully, I know it's late, but hopefully you would have at least seen that we've been doing essentially the same thing for all these problems. But I will take another class where we'll just go through these two hard problems also, yeah, with the same structure so that it's pretty clear that it's a consistent way to solve all the problems. Uh, what I did this time was I started from the overall problem definition and I made sure that the subproblem definition has the same form. But doing so didn't make things straightforward because in trying to derive the value at index I from the solution at index I minus 1, we realize that the information we need from our subordinate does not have the same form. So we have to create a new local function that each subordinate has to work on in addition to the overall global uh, requirement. And so we had to derive recurrences for both of them. But when we did so, we generally found that the G value for I was this, the previous G value, potentially updated with uh, a new local solution. And we wrote the recurrence for the local solution. Could have written the recurrence even for the global solution directly, but we would have ended up with the same thing. And we could write the local solution to the recurrence for the local solution in terms of smaller local solutions because there was optimal substructure. And so that means we could We would in general come up with two tables, two one-dimensional tables for both local solution and the global solution, which can be space optimized. So hopefully making the global solution into a variable, uh, not making it into a variable, but having it explicitly be what each manager is solving provides a better starting point than directly treating it as a variable that keeps getting updated, which is what it will do, but only when you first come up with the basic solution. Then you think of optimizing for space, both F and G. So with that, I'll stop here. Thank you all.
Want to become a software engineer at Google? You can, like thousands of our students. You just need to learn from those who've already cleared FANG interviews. At Interview Kickstart, our interview prep courses are developed and taught live by 150 plus instructors from Tier 1 companies like Google and Facebook. Our courses are tailored to help you crack software engineering domain interviews, including back-end, full stack, machine learning, embedded systems, data science, and more. To learn more, book your free webinar slot today